Thank you for your introduction, and thank you so much for giving a great opportunity, such a great opportunity to me. And hello, hello everyone. I'm Tomohiro Inada, working in ICRR in University of Tokyo, and today I will talk about the indirect dark matter studies with the Magic Telescope. And in my talk, I will focus on the review about the recent highlights with Magic Telescope. At first, let me talk about the Magic Telescope briefly. So Magic Telescope is located in the observatory located in Muchachos in La Palma, one of the islands in Canary Islands in Spain. And the height is 2,200 meters. And yes, here you can see the two telescope. Yes, I hope you can see my cursor. And yeah, there are two telescopes and Magic 1, Magic 2, so-called. And we are operating telescope from the building at the center of red building. And we have two telescopes. We have two telescopes, and both shape are identical and 70 meter diameter. And our telescope is sensitive to gamma ray from 30 GeV to 100 dB. And the field of view is 3.5, and the resolution is like this. And the right plot is the schematic view about the gamma ray detection at the ground telescope, by the ground telescope. So first, when cosmic ray comes in the atmosphere, and then they make air shower, and the created ionized particle emit the Cherenkov light. So, and the telescope at ground want to detect this Cherenkov light, and you can see the detected image like this, and from detected image, we will construct the primary cosmic ray events with arrival direction and energy. And also we can distinguish the primary particle type. For instance, in case of gamma ray, the shower image is elongated like this, but on the other hand, in case of hadron, shower image is randomly, widely distributed. So yes, this is the technique of Magic Telescope. Why? Okay. So the next is about the gamma ray signal for dark matter. So already many people mentioned about it, so I will briefly talk about it. So in case of indirect dark matter search, so we want to detect the product of annihilation, dark matter annihilation or dark matter decay. So equation is like this. So top one is equation, top one is expected flux from dark matter annihilation, and the bottom one is the expected flux from dark matter decay. And you see that like two dark matter particle annihilates into two standard model particle, and they emit gamma ray as a secondary photon, or they annihilate into gamma ray directly like this. So you can see the left bottom plot. So secondary photon spectrum and or peak spectrum. And the right part is related to the astrophysical target which we observe. So, and low is about dark matter density, and so people often say J factor, this factor is J factor. So J factor is integrated dark matter density along the line of sight. And in case of annihilation, we integrate the dark matter density, a square dark matter density. And also in case of decay, we integrate it just linearly. And there are several models about the dark matter density model, dark matter density profile. For instance, NFW, INAS, workout. The NFW and INAS belong to the Caspi profile model. And workout is core profile model. So I already mentioned in Manuel's talk. And there are several targets for dark matter search with gamma ray. And the strategy of the Magic dark matter search is the diversification of targets. So we are trying to observe. We try to observe many targets. For instance, galactic center and halo and dwarf galaxies and galaxy clusters. So they are complementary each other. So we want to make it diverse. So, and in case of galactic center and halo, apparently you see already similar plot are shown in previous talk. So this is a simulated all-sky map gamma rays from dark matter annihilation. And you see the galactic center shows clearly the highest flux, but also it's extended. And also there are many sources, so source confusion happens also, and diffuse background also there, and the Kaspi core difference about dark matter profile are there. So it's complicated source. On the other hand, a dwarf galaxy is very compact object, so dark matter dominated system. So basically astrophysical emission free, and so but relatively lower J factor than galactic center. So yeah, relatively high. So relatively high, a bit lower than galactic center, and a small extension. So that's why it's suitable for so galactic center, dwarf galaxy is popular target for dark matter annihilation studies with magic. And on the other hand, galactic cluster is in total they have huge dark matter content, but it's extended. So okay, so it's very popular target for dark matter decay studies with magic. Okay, and from here I will review the recent hour result. So one result is Ursa Major II, and this Ursa Major II is the one with the highest J factor source. You see here, and in the past analysis before Ursa Major, we analyzed the dwarf spheroidal galaxy as a point source, but in this time at the first time we took the source extension into account for analysis. So source extension, for instance, 0.3 like this, and we analyzed it. And we total exposure time is 94.8 hours. So we have plenty of good quality data. And we use the indirect refute method and limiters like this. And so almost reaches 10 to minus 23 cubic per second. And this is the right plot is a comparison with other experiment. For instance, so you can see the good complementary with polite experiment limit. And this is also the dwarf result with dwarf spheroidal galaxy and with Triangulum II. And with total exposure time is 62 hours, good quality data. And we estimated the J factor by carefully. So because this, yes, we estimated J factor by adapting shape parameter minus profile. So carefully to anybody simulation of Aquarius project. And in this source, we considered Triangulum is a point source. So we didn't consider we considered it as a point source. And analyze source size is like this. So radius squared radius is smaller than 0.02 degree square. And result and the limit is similar with Ursa Major II. So in case of variable W, the limit is reaching to 10 to minus 23 cubic per second. And now, so we are aiming to combine starting those dwarf spheroidal galaxy analysis. Yeah, we are starting those analysis. So like Segue1 and Ursa Major II and Doraco, Berenices. So those four sources have good J factor. So order is 10 to 19 J factor. So it's a good dark matter content source. And the total exposure time is reaching 355 hours. So it's a large data set. And the right plot is stacked. Those four dwarf galaxy are stacked. And you see the result is almost, yes, almost Segue and Ursa Major are dominant. And so you see that almost below 10 to 20, we are going below 10 to 23 cubic per second. So it's better result. It shows better than previous result. But anyway, yes, Segue1 and Ursa Major II are dominant. And this is from here. From now, I will talk about the dark matter decay limits. So the limits for dark matter lifetime, and with Perseus cluster. So basically, yes, in the first time, okay, thank you for it. And the first time, so Perseus cluster was taken for taken to study the active galactic nuclei in the center of the galaxy, but we recycle this data to dark matter search. So we have plenty of data, so more than 200 hours, and then we optimize the pointing and the on and off region to set dark matter decay limits. So because in the center of galaxies there is a strong gamma ray source. So we have to avoid, we have to mask this source. So we prepare this kind of on and off donuts like on and off sources or on and off region, and we subtract the background, and then we set the limit for dark matter lifetime. So and so far the most constrained lifetime the most constrained limits on dark matter lifetime more than 10 TeV. And in the last, yes, so this is also talk about result about the dark matter limit on the dark matter lifetime. And we introduce a new observation technique focusing on constrained dark matter lifetime. So we, for instance, we scanning galactic halo with fixed pointing, and then we define the on and off, and we define the region close to the galactic center as on, and the far point as defined is defined as off, and we subtract them on, and we subtract on off from we subtract each other, and we extract the residual from on. And the residual can be defined as delta K factor. So the residual can be interpreted as dark matter, as the signal from dark matter. And we set the limit like this, and so the limit is still a bit lower than Perseus cluster, but we only use 10 hours. So I think this is, okay, thank you, Maurice. This is a good demonstration for introducing new technique for that lifetime limit constraint. Okay, let me summarize my talk. So as I said, so magic dark matter observation strategy is diversification of targets. So we observe many targets. So what's the galaxy, galaxy cluster, and galactic halo. And also now analysis of another source is ongoing, like for instance, the galactic center in Milky Way, and also the combined starting dwarf analysis with other gamma ray experiments. So we Fermi, Veritas, Hayes, Fork, something like that. So stay tuned, please stay tuned our activity. Thank you so much. That's all.